building better robots. And we have Martin Mason, with Special Thanks to Robotics, who's going to tell us about how to make those robots a little better.
Thank you, Kurt. So folks, you'll be able to hear me better hopefully when the microphone gets going. There it is. Thank you. All right. So folks, I'm going to talk a little bit about building better robots, as Kurt just said. I'll give you guys just a tiny brief bit of background about me. I spend my days, I'm the chair of engineering at a college out in California outside of Pasadena. So I'm primarily involved in education. I got involved with building humanoid robots a long time ago when I was a grad student. And then again, when I took a sabbatical, I had the opportunity to work with a competition team that was doing humanoid robot competitions. And humanoid robot competitions are an awful lot of fun because these things kind of look like us. So I've enjoyed humanoid robots for a long time. And I'm going to talk a little bit about, first of all, why do makers build robots? And this is also an excuse for me to show pictures of my kid. So here's my daughter with, this is when she was about 9, with one of the first robots she built. This is a line following robot. And if you guys know, just about any major city has a robot club which has regular competitions. So she built this robot for that. Here's a picture of her with our 3D printer. 3D printer is another type of robot, right? And another thing you might be involved with is industrial robotics. Here's a picture of an automated bag printing machine from Tina Bag Company. That's a company near us in Walnut, California. They make what if you eat any kind of potato chip or corn chip that comes in a paper bag, that's printed as Tina Bag Company, right? You guys probably don't have In-N-Out hamburgers out here, but you have Burger King and McDonald's. Those bags are all printed by Zenith Bag Company. So this is large industrial process equipment. It's also robotics. You also could do robotics just to make things for Maker Faire. Last year we brought a pair of robotic lightsabers and that you could control and fight with. And so here's a picture of my kid with a robotic lightsaber. And finally, you can make robots just because they're beautiful. So I think this particular little robot is a beautiful thing. My daughter's clearly in love with it. We want to make a robot. One of the things we need for that robot, well, the first thing you need is sensors. And some typical sensors you might use would be gyros or IR distance sensors or perhaps an array of infrared sensors for line following. You also need actuators. And those actuators can either be traditional actuators like motors and linear actuators, RC servos, stepper motors. But you can also use what we call smart servos. And I'm going to talk a little bit about smart servos in just a second. You also need a way to tie those sensors to those actuators, and that's what I'm going to focus on is the controller that goes between your sensors and your actuators. So a little bit about smart servos. I got involved with humanoid robots a long time ago in grad school, and there was a fellow who kept winning the competition, and he made these smart servos that everybody wanted. And he started a company based on those, the company Robotis. What makes these servos different is on the back of every servo is a microcontroller. It's a little 8-bit microcontroller, and that continually monitors the current and the torque and the temperature and the speed. Of course, the position, which was usually get in servos. But it lets you do your PID directly in the servo, so you have a tremendous amount of control over exactly what that motor is doing at any given time. And the other thing about them is, you can see from that last picture, these servos are serial. So you can have a lot of them on a single wire. So we're using an 8-bit protocol, so you can have 255 servos on a single bus. The microcontroller I'm going to talk about has 3 of these serial buses. You can have 750 and change servos on a single robot. I've never seen 750 servos on a robot, but these little robots you're seeing here today have 16 servos on them, and if we were running pulse-width modulation, we'd have problems with timing and collision and just the sheer number of wires we need to make that work. So the microcontroller we spent a lot of time with, here's a picture of it. It's called the OpenCM 9.04. It's called open because the open source movement is still around, right? Still a lot of people very interested in it, including us. And what we did is we took the processing IDE that Arduino uses, and we ported it to run on this particular chip. This is an ARM M3 based board. As you guys know, ARM is in what's in most of your cell phones, right? And the ARM M3 is a low power 72 megahertz microcontroller. And this particular chip, we brought pins out. We wanted to keep the board small. There's 64 I/O pins on this chip, but we only brought out 40 of them just to keep the board a reasonable size. So you've got 10 analog I/O, you've got about 20 digital I/O, and then you've got some pins that we're using for specific buses, your I2C and your SPI and your CAN bus and so on. The other thing that's special about this is we put in specific connectors to run these smart servos, right? And they're really just connectors for a TTL serial bus. But we put the connectors right on the board to make it easier, and put a few other peripherals to make these easier to use. I like tables, so I threw a quick table up here. I ran benchmarks of this board versus the standard Arduino Uno. And looking at this, you see it's anywhere from about 6 to 100 times faster. And that's because it's a 72 megahertz ARM 32-bit processor instead of an 8-bit AVR processor. So just to show you that there's a significantly larger amount of horsepower here, because we're going to want to do more impressive things with a humanoid robot than we want to do maybe with an 8-bit micro. The real thing that gets to using any of these things is the programming. And that's what I want to emphasize. Here's a picture of my kid programming a robot. And I'm going to show you this. I like this slide because I'm showing you the Arduino IDE right here. It's blue. Here's a picture of the MSP430 IDE, which is a project using the TI lighting control. Yours is exactly the same except for red. Here's one that's green. That's the Maple IDE. And here's ours, which is gray. And the thing you notice is every code sample that we used is exactly the same, right? If you know Arduino, you can do this. I mean, you guys have heard of Arduino or used it before out there? Yeah, right? So the idea is, that's got the mind share, we might as well go with it. So what I'm going to do is I'm going to take you through some simple demonstrations of how we use this. We're going to drive a Dynamental motor right now, and we've got 4 ports that we can be using to drive these smart servos. And you can attach a daughter board like you can do with an Arduino. And the reason for the daughter board that we have is to drive the EIA 485 servos. A lot of industrial control stuff uses a 485 bus instead of a TTL bus or an RS-232 bus. So since a lot of the product line, these servos are very small, but the servos get bigger and bigger and bigger for industrial machines, and you want to use a real differential protocol driver. So if we switch over to the camera here, you guys are going to see that I've got here's the board, right? There it is in real life, and here's a servo that's just plugged right into that board, okay? And what I'm going to do is we're just going to go through the steps in programming this, and I've got to remember always to switch back to the screen so you can see what I'm doing here. And you guys can see this code window. I apologize the text isn't that big, but hopefully you can see it somewhat. And I'm just going to go ahead and type in a simple program to run this servo. And the first thing I'm going to do is I'm going to instantiate a Dynamental object. That's going to be one of these servo buses. And I'm going to initialize it to use the first serial bus. So there's 4 of them, right? So I'm going to choose to use number 1. That's what I've got stuff plugged into. And the next thing I'm going to do is I'm going to create I'm actually going to initialize that bus. And when I initialize it, I've got to use a particular baud rate. By default, we run these at a megabit a second. Okay? It's pretty fast. It's slow enough that we don't have to worry about wiring too much, right? And all kinds of impedance problems and reflections. But we can run them up to 3 megabits. We generally tend not to do that. You can run them much slower if you're running really long cable chains. But a megabit seems to work reasonably well for things happening all at the same time. And one of the other things I'm going to do is I'm going to put some delay in here just to give the bus a chance to initialize. And then in my loop, what I'm going to do is I'm going to use just some of the basic API commands. And I'll show you guys what those are. But a logical one is set position. That's going to set the position of the servo, and it's going to hide a lot of stuff under the rug. So I'm going to, first of all, address my servo ID. I pulled this. You guys can see, here's my robot. It's missing the arm. Here's the arm over here. You guys love to put the camera back up. That's the arm from the robot, all right? So I pulled off servo number 6 when I pulled this off. So when I'm coding, I've got to make sure I address the appropriate servo number. And I've got 2 numbers here. The first number is the position I'm going to set it to. These are centered at 512. It's 0 to 1024, so they're centered at 512. And I'm going to set the speed of 400. What we're going to simulate here is this arm's going to do some weightlifting. All right, it's going to start off flat, it's going to lift up, and it's going to go back down. And to do that, I'm just going to send 2 servo commands. My next command, I'm going to give it some delay, which is going to give us some time to get to that position. I could do something fancier and tell it to wait until it was finished, but I'm not going to bother that. We're going to put some delay so we can understand what's going on. And then I'm going to send another set position command. And I see that I told it to set positron there, so it doesn't correct my spelling, unfortunately. There we go. And we're going to, again, give the same it's pumping, it's going to go a little faster. All right? So we're going to send this out, and I'm going to put in one more delay to give that action a chance to complete, and we'll go ahead, and with any luck, I've got everything plugged in. We're going to cross our fingers. We'll see if it works the first time. We're going to download it, and with any luck, something will happen here. All right, it says downloading, and if I switch to the camera, I can't believe one of my demos actually worked the first time. I don't know if you guys, I'm active in a local robotics club, and our local robotics club has a club motto, and that club motto is, "It worked at home." Right? And we have to translate it into Latin, it's "Et Domini fungibat," right? Which means it worked at home. All right? So, it actually worked here, which I'm very happy to show. So, you guys can see, we made that servo start moving. And since this is basically Arduino compatible, the thing we want to do is we want to start adding in some external control. So what I'm going to do is I'm going to stop that from moving by just loading up a blank program. Let's go ahead. We're going to open up a bare minimum program, and we'll send that, and that'll stop it for running. Okay. And what I'm going to do now is we're going to.
It worked at home.
Remember what I was saying about it worked at home? All right. Okay, good. Now it's stopped. All right. So what we're going to do now is we're going to go ahead and add in an analog input. Okay. We said there's 10 analog inputs to this board. I'm just going to connect up the potentiometer that I've got right here, and I'm going to connect the potentiometer into this board. It's a potentiometer. It's a 1K or a 10K pot. I don't remember. I'm just going to connect it with a voltage divider. Okay. So I'm going to plug one lead into the 3.3 volt rail. I'm going to plug the other outer lead into ground, and I'm going to connect the middle of the pot to input number 1 here, just like this. I don't know if you guys can see. You can see I'm doing something here, right? And I connected this pot up. So what this is going to do is it's going to give me a value between 0 and 3.3 volts on that pin. And since this particular input is 3.3 volt input, that'll let me go to the full range of the analog input. So what I'm going to do now is we're going to just change the code we had before. And here's that code we had before. I'm going to go ahead. We've got to first of all tell it that that pin is an input pin. Okay. And if I want to tell it that that pin is an input pin, then I've got to do a pin mode command. Let's go ahead. There we go. So we're going to do pin mode. And we're going to tell it this analog pin 1, and then it's an analog, it's an input analog. And what that's doing is it's setting there's internal resistors you can turn on and off for the pins, right? And if it's an input, I want it to be a high impedance input, so I'm not going to burn out that pin, right? So this is a smart thing to do. So we're going to set those internal resistors to be on, and then I'm going to go ahead, and in my set position command, I'm going to get rid of that second one. And I'm just going to change the first one, so it's going to put in the value of this analog input. So I'm going to do an analog read, and I'm going to read that pin. And I'm going to take the value and I'm going to divide it by 4. And the reason I'm dividing it by 4 is it's a 12-bit DAC, or 12-bit ADC we're using, right? And so I want to scale that back down to the range of 0 to 1024 that I've got. Okay, so I'm just dividing by 4 to scale my values to fit into the appropriate range. I'm going to slow this down so that it doesn't jerk around like crazy. And finally, we're going to set the delay to be a little shorter so we can see things kind of move at a human rate. Okay, so we're going to go ahead. We're going to program it again with any luck. Okay, that looks promising. Switch back to the camera. So I've got my. I can see. Okay, see, there we go. It always happens. I can see what I did. If my servo, I was driving the servo into the table, and it started flashing, which meant torque limit override, and it shuts itself down, right? What you don't want to have happen is the servo to self-destruct, which RC servos will happily do, right? So this one is smart enough that if it goes over current for too long, it'll shut the servo down. What do? I'm going to unplug it. I'm going to plug it back in again, and with any luck, we'll get things to come back to life here, and we'll go ahead, we'll download that sketch again, okay, and hopefully we're going to see, I'm right? So I'm going to move my pins back, and that's what you get for doing this stuff in demos. Oh, and I've got to make sure that my analog pin is plugged into the right spot. I'll plug it in one more time. This time, it's going to be amazing, right? And we'll go ahead and download it again. With any luck, we're going to see this thing do what it's supposed to do. Aha! All right. Can you guys see that at last? I am in control! All right. So I am controlling this arm to move up and down using this potentiometer. I feel like that's a victory right there, right? Okay. So that was relatively easy as long as we plug the pins into the right spots, right? And I think the next thing we might want to do is, and I got to demonstrate that these servos are smart enough to shut themselves down. I meant to do that, right? Okay. So what I'm going to show next is we're going to hook up an ultrasonic sensor. And when we hook up this ultrasonic sensor, this is now a digital sensor. And what I'm going to say about this is that, first of all, I'm going to look at the board while I plug it in this time, right? And when I went to use this, you know, there was no handy library for connecting an ultrasonic sensor to this particular board. So I had to make a library. So how did I make an Arduino, how did I make an OpenCM9 library to run the ultrasonic sensor? What did I do? Any ideas? What's that? How? So there's no library for this ultrasonic sensor for this board, right? And I need to make one. So what am I going to do? Yes. Did somebody say, get an Arduino library, right? Yes. And that's exactly what I did. So I got an Arduino library, cut, you paste, you know, of course, in this case, I really didn't have to change anything because they're not using any timers for the library. If they were using timers, the timers on this chip are a little bit different, but a lot of the libraries will work straight out of the box if they're just banging pins and that sort of thing. So I just took an Arduino library and changed the names to fit into the bigger namespace I was using. So I'm going to go ahead, I'm going to connect this board up, and we're going to power our ultrasonic sensor. And many of you guys have used these sensors. They just use 3 pins. They've got power and ground, and then they've also got a trig and an echo pin. Okay, and that trigger pin triggers an ultrasonic pulse that's going to go out, and then you're going to wait for the echo pin to go high when it receives the response. Right? So they're very simple to use, and you just measure the pulse width of the echo pin to figure out how long the signal's been out. And I want to make sure I plug this into the right pins the first time. And I'm even going to check in my code to make sure that I matched it up. So I plug this into pins 8 and 7. And it says the trig is supposed to be 8, 7 is supposed to be echo. And I've got trig plugged into 8. And I've got echo plugged into 7. So with any luck, we'll get this to work the first time. So I'm going to go ahead. We're going to modify our code a little bit here. So that same exact motor control code, we're just going to change it so that instead of looking at that analog input, we're now going to look at this ultrasonic sensor. I've got to do a little bit of work. I should have brought my mouse, I think, right? I got to do a little bit of work to initialize the ultrasonic sensor. And what that includes is first, I've got to include the library that really is just that Arduino library we talked about, right? What's that? Oh, so sorry about that. All right. So since this is C, I've got to remember to use include instead of import, like it was Python. So we're going to include that library, and you guys can help check me for typos as I go. The name of the library is ultrasonic. All right. There it is. So we've included that library. We've got our Dynamixel being set up. I'm going to create an ultrasonic object. Okay. And I'm going to call it distance sensor. And it's going to be on ports 8 and 7 for trig and echo. And we're going to go ahead. We don't need to do anything in the setup to set up that sensor because we created the object. And this object has a function called read distance, which we can call to get distance as well. Okay. So we're going to set the position of our servo to the distance sensor distance. And I'm going to go ahead and multiply that by 3 because it's a distance of centimeters, and you know the ceiling's way up there. The sensor's not going to go that high. So I'm going to multiply it by 3, and then I'm going to go ahead and I'm going to add 500 because I don't want that problem with this driving to the try it again. All right. And as you guys know from Arduino, sometimes it resets, sometimes it doesn't, and sometimes you just make a typo. And I suspect mine has something to do with how many parentheses I used. I see an extra one right there. Okay. And we'll go ahead, we'll try this again. And now with any luck, we'll switch back to the camera. And, oh yeah, I'm already at the camera. So can you guys see if I raise my hand up, the arm is moving up? Oh, that's pretty amazing, right? Well, I think it's pretty neat, right? So I'm controlling this arm using only the power of my hands. All right. So, and if I let go, it's now seeing the ceiling, and it's going to go up to the maximum height. Okay? All right, so we've seen a lot of stuff. I just took an arm off this robot. And what we can do is we can combine all this stuff to make a robot do really interesting stuff, right? So the last thing we're going to do is we're going to do a demo for you. So, Aaron, if you'll come on up, he's going to start this demo up while I'm saying the last few words about this. And just while he's setting this up, there's a whole API that gives you a lot of commands to talk to these different servos. And you can talk to them at the high level, like a set position, set goal position, set velocity command, or you can write words to the table. And just to give you an idea, I like tables. There's a lot of data that you can get back to these servos and send to these servos. So I'll flash through that real quick. We're going to put it together in the robot right now. Are you ready here? All right, so I'm going to need a 5 count. Can you guys give me a 5 count coming in? All right, 5, 4, 3, 2, 1, go! It worked the first time. It's a reasonable price if you want to get